It's 12:45, so we should probably get this started. Welcome to the fourth and final day of 26C3. Please all welcome Hunts. He's giving a talk on finding the key in the haystack, a practical guide to differential power analysis. He will be discussing the fact that most consumer products with microcontrollers do not do a very good job of shielding the power emissions, and therefore you can figure out what kind of data it's processing by differential power analysis. He plans to discuss the basics of it and then go into a little more details about how you can mount such an attack on consumer products with these kinds of common microcontrollers. So please give Hunts a round of applause. Thank you.
Hello. So we'll just start with the topic. And a short overview. I'll do a little introduction first, and after that I'll explain the measurement setup and the procedure of the measurement and the parameters you can tune and you should tune. And after that we'll go into the analysis details, starting with an overview, and then the remaining points are very analysis specific. I'll get to them in this section. So what's DPA? It's a side channel attack. It was introduced by Paul Kocher, 1998, and it is used to recover secret keys during encryption or decryption. And one point is you have to know the algorithm, so you can apply a DPA. And the DPA works by measuring the current consumption. This consumption of the device depends on the data that is being processed. And thus the current measurements give hints about the internal data. And so we can be able to find the key. But the key can't be found directly in the power consumption. It is somehow like the search for the needle in the haystack. So you need some recovery or extraction method, and this is basically what DPA does. The basic idea is, in this talk we will attack encrypt function with 128 bits IS. And the brute force, well, this would take a while. I guess I don't have to explain this. And with DPA, we can do this faster. We don't have to guess all bits of the key correct at the same time, but we can do portions of the key. We can go for each byte. And so we can recover the key byte for byte, and this leaves us with about 4,000 keys we have to try. But to do this, we need to encrypt several plain texts and measure the current consumption during this encrypt. This is in the range of about 100 up to a few millions is also possible. It depends on your measurement setup, on the noise, and on countermeasures and whatever. But in our example, a few hundreds will be sufficient. A few more notes before we start. This is not, we won't attack a flaw of the IS encryption algorithm here. Side channel attacks are a problem for every crypto algorithm, or for nearly every crypto algorithm. And unless the implementation, the programmer is aware of this issue and does the implementation with countermeasures. So you have to program in a certain way to avoid this DPA or other power attacks. And there are usually no countermeasures in standard consumer devices because the countermeasures are expensive. You have to pay license fees if you want to protect your hardware. They're nearly all patented, so you cannot protect your implementation unless you pay this license fees. That means that most consumer hardware is vulnerable to power analysis attacks, this doesn't affect the smart cards. Here high security is needed and the license fees are paid, but not for the consumer hardware. Still, power analysis isn't yet widespread in the hardware hacker community, as far as I have seen. And this is interesting because it ain't no rocket science. We will see this in the talk. So let's start with the measurement setup. Here we have the device we want to attack. I'll refer to this as the device under attack, DUA, in this talk. This is here to be seen. And here we have a level shifter and an FPGA board, basically for controlling the device, for sending plain text to it, and for generating trigger for the digital storage oscilloscope. We can see this here. This is used to measure the current from the device. And here we have a laboratory power supply to power the device under attack. Basically, here you see the same thing in a more abstract way. Here again is the device under attack. It is connected to some kind of control interface that connects it to the PC, so we can send plain text to the device under attack. Or if the device generates such plain text itself, we can tell the PC when a new plain text arrived and which one. We need the plain text, we need to know it. We don't have to craft specific plain text, but they should be mostly random. Now the device is powered, of course, and we need to measure this power. This is done using a sensing resistor. We measure the voltage drop across this resistor with the digital storage scope, and we can read the power samples from this scope afterwards. We also should use an external clock source to synchronize the device we want to attack on the digital storage scope. I'll come back to this later. First, let's have a quick view of the measurement procedure. The first step is we configure our device we want to attack, prepare it for N or decryption, set the plain text, and so on. And then we set up the trigger on the digital storage scope. And finally, we give the start instruction to the device. Sometimes point 1 and point 3 are the same. So for a smart card, for example, you just send the data and it starts right with the encryption. And after the encryption is done, we read the power data from the scope and do the same again several times until we get all the measurement we need. So of the points of interest here in the measurement setup are the power source, the clock source, the resistor, and the scope, of course. This control interface is mostly specific for the device we want to attack, so you have to figure this out somehow yourself. It depends on the device. The sensing resistor is, as the name already says, for sensing the current used by the device consumed, and we measure the voltage drop across this resistor. Usually that is 1 up to 10 ohms, fine. And we, of course, if we take smaller values, we will have less drop, so the device will be less influenced by this drop. But we often need to use higher resistor values because of the measurement precision. We'll get less precision if we use a smaller resistor, then the drop is smaller, of course. So you always have to choose a bit and play with this value. And if the drop across the resistor is too high, you often can increase the voltage supply a bit, but be careful so not to fry the device. Also, it is useful to use resistors with low inductance here. So wire-wound resistors are a bad choice because of their inductance. And we can insert the resistor basically at ground or at the voltage supply side. You just have to choose the ground of the scope wisely, and this should be then rather the voltage supply should be the ground of the scope or the common ground. You have to be careful here, so you won't get any short circuits with your control logic if you use the voltage supply side. This is why ground is usually the easier way to go. The digital storage scope should have a sample rate of at least 250 megasamples per second. This doesn't depend directly on the clock of the device or on the maximum clock of the device you want to attack, but it would consist of the maximum clock for the interesting parts that leak into the current consumption. So where the key is processed. And this is usually very high frequency, but we won't get this high frequency outside of the integrated circuit because there's a lot of internal capacitance and this will block the high frequency. Thus it is sufficient to use lower sample rate, but you shouldn't usually go below 250 megasamples. The sample buffer is another important thing. It should be rather in the megapoints range than in the kilopoints range. For example, if you only have 4 kilopoints sample buffer and you sample at 250 megasamples per second and your device is clocked to 4 megahertz, your buffer is just sufficient to record 66 instruction cycles of the device. This may be sufficient for hardware IS implementations, but in software, in our implementation, the complete run will take about 3,000 cycles. So we only need the first round, but this is still the factor 4 or so. Of course, if you can't afford a higher priced scope, you can still do the same plain text and trigger at different offsets and then splice those traces together. But it is, of course, more work. Well, the picoscope is a storage scope that is that isn't quite so in the high price range, though it has a quite good sample buffer. It has 32 megapoints, that is usually quite expensive, and 250 megahertz analog bandwidth. You have 1 gigasamples per second, and it does 100 megavolts range. With the 10 times, you have to get this bandwidth, you have to use the 10, the division setting 10, so you'll only get 2 volts, and this is this precision is not very good anymore. Yeah, I'll come to that. I don't have an active probe here. They're quite expensive. We'll come to that immediately. You have to try to use the full range of the analog digital converter by adjusting the sensing resistor. If you use a higher value, you'll get a larger drop, and this is, can be measured in a better way. And you can increase the supply voltage, so the current will also increase. And if you're lucky enough to have a diff probe, then you can use that. It's really nice, but they are quite expensive as well. We're trying to build our own low cost based on differential amplifier, about 100 megahertz bandwidth or so. But we aren't so good in the analog things, so we can appreciate help there. If you want to help and can, please drop me a mail. Okay, voltage source is also important. Disconnect the onboard supply, especially if there are switching supplies on board, and use your own. If the device is powered with multiple clock sources, it's usually the smallest one you have to choose because this is the power for the internal logic. Lab power supplies often have more ripple than one might guess. You can measure this at a resistor. And so don't use step downs, use stick cables, capacitors, short cables. The capacitors, I will come to them later again. And a good choice is also rechargeable batteries and low noise linear regulators. For example, I've added one from National Semiconductors here that had has a pretty low noise. And you shouldn't add variable resistors here, because if you touch them, they will be configured otherwise. So slightly higher voltage supply often won't hurt. I've already mentioned this, as there is this drop across the resistor, and we have to compensate for this a bit, but not too much, or the device will be broken. The capacitors should be placed as on the right side and not on the left. The left side is as it would be if you modify a PCB and add the resistor, but this will do no good for your measurements, so you should add the the capacitor parallel to the device and the resistor. And use ceramic resistors. They have a much faster response, so you won't block the high frequencies. The clock signal should be a CMOS signal to avoid ringing, and you can do this using a series resistor to get the edges smoother, or you can just use an external clock source like a function generator and sync it with your scope if your scope has this possibility. Otherwise, the clock of the device and of the scope, they will drift and jitter. A workaround is stretching the cycles in software by aligning the edges of the current peaks. Okay, two other points regarding the clock. A higher clock is better if you have not enough sample buffer, because you will waste less sample buffer, obviously, if you use a higher clock for your target device. And a slower clock will give you often more stability in case you remove the capacitors. Let's just have a look at two power curves. Here we have a bad example. One cannot see steep edges here. A slower clock often helps here to get the edges sharper, and we have such an example here. Often the logic, you can see the rising and the falling edges of the clock here. Usually most of the processing is done on the rising edges. This is also the case here. It's an 8-bit HVR microcontroller. And here we have a rising clock edge. Oh, it's not shown here. This is the power trace. And here falling edge, rising edge, and so on. Don't ask me what this bump is. I have no idea. Here we have two different power traces. One can, with different plain texts, so one can see that they differ hardly. That's why you have to measure with so many plain texts to get the result. Okay, very crucial for DPA to work is proper alignment and synchronization. That means at each trace, every instruction needs to be at the same samples. So if you put those traces down like in this picture before, they should be aligned in a way that they completely overlap. And this is crucial, as we will need this for the analysis. And precise triggering, the first step is external trigger source for the scope, depending on data or whatever you can use to generate this trigger. And the next step is pattern matching at the computer to align those traces after recording. The majority of the dynamic current we see in those traces here is not data, but instruction dependent. That's why you can align them well using pattern matching techniques. One method is the least squares. So you just move those two traces against each other and sum the squares of the differences between those two traces, and you pick and you take that setting where you get the least sum. If you've done everything right, you should see the rounds of the AES algorithm. Here you can see the first 7 rounds. There are 10 rounds, so this can be identified quite nice on the scope. And another point you see is that the AD range is used very well here in this picture. So let's get to the analysis phase. How does TPA work? We have a constant unknown value, the key, and we can't recover this key directly from the power consumption without profiling the device. That is what template-based power analysis do. We won't do this in this talk, but just so you have a keyword for Google. TPA does recover the unknown constant data, the key, by analyzing its influence on known variable data. This is, in our case, the plain text. It can also be the ciphertext if we do the decryption. We will do the encryption here. The original method was introduced by Kocher as the difference of means. I won't explain this method here, but rather I will do the analysis using the Pearson correlation. This is a more powerful method, and I'll spare you the formula here. You can find them on Wikipedia. I put the links in the slides. They should be in the, on the website now. So the short version is you guess a part of the key, a short part, and you use this part of the key in combination with the plaintext that you know to evaluate the encryption function and get some immediate values that occur during the encryption routine. And these immediate values you can then use to estimate the power, and then you verify this estimation with the actual consumption measurements. So you know the key is correct or it isn't. If it isn't, we'll guess new, and we'll take a new guess. That's basically the thing. The most important question here is what is a suitable intermediate value? We need those to verify our key guess. And to answer this, well, this is the answer. You look at the function we want to attack, and you search for 3 keys. You need an intermediate value that depends on both the key and the plaintext. We want to recover the key by observing it getting mixed with our data. And the intermediate value should depend only on small portions of the key. We have to guess those key portions after all. So the exhaustive search otherwise would be too costly. And this intermediate value also should exhibit strong variation, even for little input variation. So if 1 bit toggles in the plaintext or in the key, the output should toggle with more variation. Otherwise, we won't be able to get everything right, because we won't see such tiny fluctuations in the power supply. We'll come to this later again. Okay, let's have a look at the AES encryption. This is a general AES encryption. It's done that way every AES implementation. In the first round, we have a round key, so each byte of the plaintext is XORed with the same byte of the key. So key byte 0 gets XORed with plain byte 0, and so on. That's could be our intermediate value. It actually depends on the key and the plaintext. It also depends on small portions of the key on 8-bit blocks. So, well, this looks nice, but we don't have strong variation for little input variation. If 1 bit toggles only if 1 input bit toggles, we will only be able to observe 1 output bit toggling, and this is bad. So we continue our search into the next block of AES, and we'll see that this is the subbytes function. Here the S-box access gets done, and this intermediate values from before get thrown into the S-box, and for each there will be they will be replaced with the value of the S box for this particular intermediate value. So we have a new candidate here, and this candidate is actually very good because of the S box properties. So a good S box has the property that if you toggle one input bit, the chances for each output bit to toggle are 50-50. So we will observe strong output variation here, even if only one input bit toggles. The next question is, how do we verify if we did guess that this immediate value correctly using the power consumption? To do this, we need some kind of model to estimate the power consumption depending on data. Here we have CMOS logic inverter with input and output and two gates. This is complementary logic, so we have P and an NMOS, and we have some capacity at Q because at the output because there are other gates and traces. So we will see current if the gates toggle. If the input changes, these gates will be, one of them will be charged and one will be discharged. And this leads to two effects. The first is that the gate charging needs a bit of time. And during these chargings, both of them will conduct a bit, both of those transistors. And we will see a certain short circuit current. And the other thing is that this output gets charged or discharged, and if we see it get charged, we will observe current consumption as well. So basically we can see changes between zeros and ones in the power consumption, but this is only an approximation, of course, because we don't know the length of the traces within the chip. We can't make an exact model of this. So our approximative model will be the Hamming distance model. We just we just count the numbers of bits that changes between two variables. Here we have 101 and 1 and 011, and so 2 bits toggle. We have a Hamming distance of 2 between these two values. This is fine for registers. So if you want to model registers, this is a fine technique. It is also it works very well with hardware crypto units. The problem is that you need to know the previous value. So this is not always the case, and it is implementation specific. So you can't apply this every time. But let's have a look at our HVR AES implementation. Here we can see first the round counter gets initialized, and then that round key gets called, and now it does the S-box access. Here, most of you probably know HVR assembler a bit. We have 3 16-bit counters. One of them is set, and we have the higher part and the lower part both being 8 bits. And the S-box is at a constant higher part. It's just a lookup table with 256 values in it. And to access the correct byte, we use this ST11, which will be our I value, and we load the byte from this I value. So this is the lookup table access. Now, if we think back to the I values, we have this at round key here, and we have the S-box access here. And we see that the register ST11 gets overwritten by the output of the S-box, for which the input is actually also ST11. So we know the value, so we write the value from before the S-box, we write the value from the S-box access above the value from before the S-box access. And this is perfect for our Hamming distance model. We can model this way, and we know both values, so we can apply the Hamming distance model here and get the current consumption approximation. Another application of the Hamming distance model is hardware crypto units. You often have a register after the S box, and it gets updated each time you pass something new through the S box. So you can compare the outputs for two different immediate values that get written to the S box. There are 16 X box accesses in each round, and you can compare the output of two of those. Which two depends on the actual order of the S box accesses. So you have to play with those values, and you also have to guess 2 bytes of the key at the same time. But this is just a tiny note. If you ever want to attack a hardware IS encryption, you can think back to this slide and try it. Now another current consumption model is the Hamming weight model. Here we have the Hamming weight of a variable is the number of bits that are set to 1. So the Hamming value of 101 will be 2. This often helps if we don't know the previous value of a register, and it works as long as this previous value is constant. It is also fine for software crypto implementations because there are often large data buses within microcontrollers, and these data buses then need to get charged if they toggle to 1. Now let's apply the Hamming distance model to our implementation. And here we have decided to use those 4 plain texts. Each plain text is 16 bytes. We'll just only consider the last or the first byte. If you this byte of the plain text, the other 15 are can be done the same way. So we'll focus on this byte, and we have those 4 plain text values, and using our guessed key 0. This is also only 1 byte of the key. I already mentioned we do this byte-wise, and using this key value, we can calculate the immediate value and the S box of the immediate value. We get, okay, I see those aren't updated. There should be, you can do this as your homework also. Actually, the output of the Hamming distances does fit. It's just the wrong numbers here in the Hamming distance function. Okay, so we get our power estimations for this register being overwritten with the S box output of this register. And now what we do is we make some kind of stencil from this. So we estimate the power consumption. Okay, power consumption 4, 2, 6. We'll use the stencil immediately. Now we have our power traces. This is, here we have more power and less power, and this is the x-axis is the time, the samples, and the y-axis is the value of the power being consumed. We already said we do 4 plain texts, and so we get 4 power traces. And well, each one here is a cycle, each peak. Usually you have to take every second because of the falling rising edges varying. And now we use our stencil from before. And we apply the stencil and move it across the traces and see how well our stencil fits to the power traces. And so we move it here, and now we go down and see how well does this fit, how well does this here fit, how well does this here fit, well does this here fit, and the overall correlation value, so how well does it fit, we note down here. And we do this for each sample of our traces. We move it here and calculate this, and what we get is a correlation curve. That this we have again on the x-axis the samples, and on the y-axis we have how well the data we have in the current, how well the current data fits to our stencil. Here it didn't fit very well, obviously. There's just a bit of noise for the key value of 0. So we'll take another guess and use the key value 1. We also compute the same thing. You again ignore what's here, and we make a new stencil based on these values, and we do the same again, move it across those power traces, and here we will see that it surprisingly fits very well here at this specific cycle. So our correlation curve will look like this. Okay, and this is where our intermediate value that we predicted got actually overwritten exactly in the way we predicted it within the microcontroller. This does our correlation curve tell us. So I have some real life examples of correlation curves here. Here is the Hamming distance correlation example for the correct key guess. And you can see here is one tiny but large peak. So it is large on the epsilon axis, but tiny on the x-axis, because it is only one single cycle. And this is the cycle in which the register gets overwritten. And it doesn't appear again. Here we have the samples again, and if we use another key, then the correct one, we won't see this peak. It will be only the noise we can observe afterwards without the peak. Okay, so much for the Hamming distance. Let's zoom in on this a bit. We cannot see it very well on the beamer here, but you can have a closer look into the slides. And here I've put the correlation curve across the top of the power curve. And you see, also here is the instruction denoted. You can then align the instructions with the power samples, and you see exactly at which instruction your intermediate value, the predicted one, occurred. To write the instructions here, you of course need some kind of reference. I did this adding a trigger output to the IS encryption routine, so it will switch one output to 1 each time the AES encryption starts, and I can count the cycles through the assembler instructions, and then I know exactly at what time in the power traces or in the correlation trace which instruction is executed. Another example for a correlation curve is here the Hamming value and the Hamming weight. And we see that this does correlate at several points. It's actually in the mix round function of the IS encryption, and it is correlating way better than the Hamming distance. We had 0.6, 0.5, yeah, and here we have 0.8. This is very good correlation actually, because the maximum is 1. And if in case you're wondering what negative correlation does, it says you predicted exactly the opposite of the actual value. And you did this every time you predicted the opposite. So it is also correlation, but negative correlation. This is also fine. And because it also tells us the key is correct. So you can use the absolute value of the correlation. Okay, a short note on decryption. The cipher text instead of the plain text is used to attack the decryption function, and the decryption function is the reverse round order. So we start in the 10th round and get back to the first round. So we cannot, I forgot to say one thing. In the encryption function, the round key for the first round is the actual IS keys. The other round keys are derived from this key using the key schedule. and we could recover the actual AES key during the encrypt function, because the round key for this function is the AES key. This isn't the case for the decryption. Here we'll start with the last round key, and so we can't recover the AES key directly, but we have to make our way through each of those rounds to get back to the AES key. So this is way more complicated. It is basically, you just need some more analysis steps, and 16 times the 4,000 keys in the worst case. And because you always have to require, you need the round keys of one round to get to the next round. You can't just get for the last round, because your intermediate values of the last round will depend on the intermediate values of the round before and back to the first round. So you have to go all this way down. So yeah, I already told this. The conclusion is basically that nearly all crypto implementations in consumer products are vulnerable to power analysis attacks because of license fees. And power analysis can basically be done at home. It's no rocket science. The analysis is well understood and published in the scientific community for years. You just need adequate digital storage oscilloscope with a bit more than usual sample buffer. And this makes this hobby kind of expensive bit. But it should be at least affordable for hackerspaces. So the picoscope I mentioned is about 1,800 euros, so about the costs of a notebook. You have to be patient. It won't work at the first time. You have to play with the measurement setup, find noise, reduce noise, try some other parameters, try another resistor, and so on. You'll find a lot of fault sources you have to remove before going on. And the best way to not have to remove this fault again is writing it down if you see it. So if you change anything, a resistor or whatever, a setting, write it down and also write down your observations. Otherwise, you will do the same thing again if you have another device or setting. Also, before attacking black boxes, that is foreign hardware, which you shouldn't attack anyway, you should go with your own implementation, like here I did with the AES implementation, because here you know the exact implementation and you can very well try this then and optimize your setup before you attack real targets, which you shouldn't. Okay, some references. There is a very good book regarding several kinds of power analysis attacks. Also, the template attack is here explained. There is a smaller power analysis tutorial, and here is the original paper from Kocher, and the AES implementation I used in this example. I also put a link for this. You can have those links in the slides. Some Wikipedia articles, and I've put my C code for the analysis of this AES encryption data in a Google Code project, so you can try this stuff. And you just have to download 112 megabytes of power traces, so this is 500 power traces, and you can just use this data to test the whole thing. It's C code. Maybe this is one of the reasons why the hacker community didn't use it before. There was an actual open implementation, but you had to use MATLAB for it. So I hacked this in C, and it works, at least for me. Yeah. I also started, I wanted to do this talk a bit earlier than, I wanted to make the slides a bit earlier than I thought, and I started a Google Wave. So we can still use this Google Wave if you have questions to, regarding the sample code, one tiny note. I don't know if I wrote it down somewhere. The Hamming weight should work to recover the complete key using those samples. The Hamming distance does not work due to optimization in this code. You don't have this particular code that loads the SBox input and the output like I showed in the slide above. This doesn't work for all outputs, so you can't get any key value with Hamming distance, but Hamming weight should work. Yeah, basically that's it. Do we still have time for questions?
You have 15 minutes.
Ah, no, that's good.
Ask questions. There's a microphone right there. There's a microphone on the other side. Please line up behind the microphone and ask questions there so we can pick that on the recording. Thank you.
I have a question. Do you know if DPA, right here, do you know if DPA is applicable to TPM chips? And did you try it?
No, I haven't tried it. But for DPA chips, you mostly would attack RSA encryption, I guess. So you need other immediate values, and I haven't done this yet.
Okay, what about the sampling oscilloscope? You complained about the memory width, and you sampled, for example, with 200 mega samples, and you have a clock rate of 4 megahertz. So this is too much oversampling. So I would recommend you to make a PLL and make some clock divisors, and so you can do it with your FPGA, and then you can, for example, please turn the volume down, then it won't be a feedback. Okay, so if you then generate a smaller clock for the scope, you can clock every scope from external source, and then you can save memory. For example, maybe you clock with 10 megahertz the scope, and then you clock the CPU with 1 megahertz, and then you can see something.
Yeah.
And so you can be more economic with your memory.
Yeah. Okay.
Do you think, is this also applicable for RFID devices?
Yes, you can attack RFID chips basically with the same technique, and well, you have more noise if you use the original antenna setup. So you would have to record more traces, or you cut off the antenna and you supply it with a sinus signal via a resistor. This should also work.
Have you tried to use Hall sensors for the measurement of the current?
And please again.
Do you have to try to use Hall sensors instead of the resistor to measure the current?
All setups of resistors, so different values, or you mean voltage supply or ground, or
No, is it possible to use a Hall sensor
no.
to measure it?
So with inductive,
Yeah.
yes, I used it, and with a tiny coil, so I built one myself with 2 windings, and it worked well with the HBR, but it doesn't work well with particular higher clocked devices. That's why I usually stick with the resistor.
Okay, thank you.
If you have a little bit money, you can buy current probes from Tectonics, for example. They have bandwidths from 100 megahertz, so you can measure currents from 0 to 100 megahertz, and you can buy such current probes. But you could also take a small resistor, take a high bandwidth operational amplifier, and then you are finished with this problem, measuring currents.
Yeah.
And you should always ground at the resistor, the scope ground, signal ground, because it's the source of the signal.
Yeah.